Hello everyone and welcome to another day of PChem. So today we are going to be finishing up our conversation on symmetry. So last time we went ahead and examined how we could use symmetry to help us solve integrals, especially those that were focused in on the overlap between two orbitals. And this one is really important as it really helps us solve a lot of problems from MO theory. But it turns out that most of our integrals in quantum mechanics tend to include operators. So we also have to figure out how we can build in our description of operators into our discussion of symmetry. So uh, most of our integrals with operators tend to fall over one of two general forms. So either we're doing something such as using an expectation value, where my two wave functions contain the same value, at which point we will know that they will have the same symmetry. And the only time we will have a non-zero value is if my operator is of the asymmetric form. The other case, which we do run into occasionally, is when I and j are going to be different wave functions, at which point it's going to be very important for us to determine the exact value of the exact irreducible representation of our initial and final wave functions, and also the irreducible representation of our operator. So we'll need to know all three of these things. So we're going to go ahead and start by looking at one of the more important operators we've talked about this semester, and a bit of a throwback. Let's go ahead and look at the kinetic energy operator. So the kinetic energy operator for the total kinetic energy of a system can be broken up into the kinetic energy in the x, y, and z direction. And we can also express this in terms of a prefactor times the square of the angular momentum, or sorry, the square of the linear momentum in the x, y, and z direction. So what we're going to need to do in order to evaluate the irreducible representation of our kinetic energy is try and determine the irreducible representation for each of these operators. So let's go ahead and start in on the irreducible representation for our kinetic energy just in the x direction. So we know that our kinetic energy will end up being proportional to applying the square of our linear momentum operator. Now, in order to figure out the irreducible representation of our linear momentum operator, we have to be working in a certain point group. So, for example, let's go ahead and work with our old familiar friend, the C2V point group. So again, in this case, our momentum is headed in the x direction. And so all we need to do is figure out who is the x direction. So in this case, we walk down our character table and we find, ta-da, that's going to be our B1 irreducible representation. So in this case, I know that the momentum belongs to the B1 irreducible representation. But there's a slight issue here. I'm not looking at so much at the irreducible representation of my momentum, but my squared momentum. So this could be seen as multiplying the B1 representation times itself, which will always give us back our completely symmetric irreducible representation, or our A1 group. And you can see this over here in the D column. If I'm taking the square of my x direction, y direction, or z direction, this will tend to give me my A1 irreducible representation, and it will always give me my completely symmetric irreducible representation. So what we note here is actually something that's very important. It's going to be the fact that our Hamiltonian will always belong to the completely symmetric irreducible representation. And this is actually very important, because what it means is when I'm considering the symmetry of operators, such as looking at resonance and Coulombic integrals, but specifically at resonance integrals, it means that I'm only going to have a non-zero value for the energy if I and j belong to different belong to the same irreducible representation. So this actually adds a little bit more importance to what we talked about last time. That I'm only going to have an energy of interaction if my overlap integral is non-zero. So in other words, if that interaction is symmetry allowed. And this is one of the reasons why when we were working in Huckel theory, we were able to treat the pi system and the sigma system very differently and entirely separately because they belong to different symmetry groups. And because there was they were not allowed to interact according to symmetry, it means that there was no interaction energies, no overlap integrals, no resonance integrals, and thus they were indeed completely separable. But we have to actually apply these consequences of symmetry in order to prove that. And this is actually fairly important because, again, we did this with the kinetic energy, but it turns out that this will hold generally for most Hamiltonians. And there is a reason why Hamiltonians tend to contain a lot of squared terms, whether it's position squared in the potential term or momentum squared in the kinetic energy portion. This will help us preserve the fact that Hamiltonian is going to be completely symmetric. And if you walk through some of the examples throughout the semester, you'll see that this holds fairly well. But there is actually another major category of integrals where we're interested on applying an operator to two different wave functions. And this is actually photoelectron spectroscopy. So if you remember, way back to the end of our atomic orbital theory, we were looking a lot about atomic electron spectroscopy. And in that case, we were looking at very much forbidden and allowed transitions just using angular momentum. But it turns out we can also apply symmetry to help us make some of the very same arguments. And we actually start with the same equation, and that's the transition dipole moment. So as we saw previously, our transition dipole moment is going to convey a lot about the intensity of our signal. So if we have a transition dipole moment of 0, this is called a forbidden transition. So previously, we were using conservation of angular momentum to show that by applying Q, or our photoelectron excitation, that we could figure out what excitations were allowed or not allowed. And we're going to be doing something very similar here. And we're going to start with the same point we made then, which is that Q is going to tend to be oriented around the X, Y, or Z axis. And so what you can do is, depending on the point group you're looking for, you can find what irreducible representation corresponds to X, Y, or Z, and use that to figure out what product of these three functions are going to give you a non-zero value. So again, if we know the symmetry not only of our photon, which has three possibilities, but also of our final and initial wave function, we can figure out which excitations are going to have a zero amplitude and which ones will have non-zero. Again, if these three functions have a symmetry besides the completely symmetric representation, this will again give us a zero amplitude, and we are going to refer to these as symmetry forbidden transitions. So let's go ahead and, since this is a little bit abstract, let's work a concrete example. So let's go ahead and work our classic C2V point group and try and determine, can I have an excitation from the px to the py orbital. So sorry about this. So we're going to be looking from an excitation from px to py. So in this case, what I'm going to want to do is take a look in my table and figure out what all of the symmetries, what the irreducible representations for each of these three terms are. And we can almost rephrase this question. Is that what product of these three species will give us the completely symmetric irreducible representation, or what product of these three will give us a value of A1? So let's go ahead and assign an irreducible representation to each of these three terms. So in the first case, we'll have px, which I can look up here and find that it's going to be the B1 irreducible representation, and then Py, which is going to give me the B2 irreducible representation. So these two are going to stay fixed. Now what I'm going to be doing is trying different values of Q. So as I said previously, this can be oriented along the X, Y, or Z axis. So we're going to try each one of these individually. So we have the photon being oriented along the x-axis for B1, the y-axis, which would be B2, and the z-axis, which is going to be A1. So now I have to try and solve each one of these symmetry products. Now this is where we can use some of the rules that we've developed so far. So I know that any irreducible representation times itself will give me the completely symmetric irreducible representation. So in this case, I know that B1 times B1 should be the same thing as A1. But I also know that the completely symmetric irreducible representation times any other irrep will give me that other irrep. So A1 times B2 gives me back B2. And we can apply the same logic here. B2 times B2 gives me A1 times B1 gives me B1. So congratulations. A photon coming along the X or Y axis will be a symmetry forbidden excitation. But we still have one last Hail Mary. We've got the Z axis. So we can proceed this, solve this one via one of two ways. So I can apply A1 to B1 or B2, essentially letting me drop out the completely symmetric representation. But that still leaves me trying to determine what the irrep is for B1 times B2. So what we're going to try and need to do is try and determine the product of this particular interaction. So we're going to do this one manually, just as a good refresher. So I can go ahead and show that I can do a product of 3 separate irreps. So I'll line them up, 1, 2, 3. Then 1 times 1 times 1 gives me 1. -1 times 1 times -1 will give me a value of 1. Now in this case, I only have a single negative value in each axis. So my product is 1, 1, -1, -1. Turns out we've more or less done this one before. This is our A2 irrep. Notice I can immediately identify it as A because it is completely symmetric upon rotation and the identity. Now, here's our problem. Since our product is of belongs to the A2 irrep, this also means it's anti-symmetric to integration, which means any integral of the A2 resulting function is going to give me a value of 0 when integrated over all space. So congratulations, we've shown that excitation along electron excitation between the px and the py orbital is going to be symmetry forbidden, no matter whether the photon comes along the x, y, or z axis. However, you can actually conduct a very similar procedure and find that excitation from either the px or the py orbital is actually allowed if it's excited into the s, the pz, or the dz squared orbital, which shouldn't be too surprising because all 3 of these species belong to the completely symmetric representation. So in other words, you can excite from B1 or B2 into A1, which is actually a fairly cool trick. So this more or less brings us to the end of applying of our tour de force through symmetry. So next time, we're going to be picking up a quick rundown of some of the highlights of spectroscopy. It'll be a little shorter than I'd like, but until then, take care and stay healthy.